Let's continue with the intro probability example. One thing I wanted to show, I forgot I had the snipping tool here. I snipped the picture of the probability density function. This is the kind of picture we want to have in our heads for thinking of the interpretation of what is the height of this curve mean. It means it measures the probability of a given little sliver of the probability divided by how wide a margin of error we look at. So now with f, we're trying to find the mean waiting time. Before we start calculating this with integration by parts, we'd like to just guess. Do you think it's bigger than pi over 4, halfway, or less than pi over 4? Think about it for a second. Well, hopefully we're going to get an answer that's bigger than pi over 4. If it's more likely that we get we wait a long time, on average waiting time, we'd be very surprised if it was pi over 4 or less. So that's a good hint as to sort of checking our answer here. Okay, so let's look at the setup here. U is going to be t. We're going to do integration by parts. And then dv is going to be sine t dt. Okay. So then du is going to be dt. And then v is going to be minus cosine t. All right, so we're ready to set it up. So this guy, let me just copy and paste that again. Okay. That guy's going to be equal to uv, which is minus t cosine t, evaluated from 0 to pi over 2, and we'll see what happens with that in a minute, minus the integral, still from 0 to pi over 2, of v du, which is down here. So that's a minus cosine t, so that'll change to plus, and this will be cosine t dt. Okay. Now notice, when t is 0, this dies, and when t is pi over 2, cosine dies. And so that actually dies. Not super common, but it does happen sometimes that what's called the boundary term in integration by parts just dies. And then integral of cosine t is just sine t from 0 to pi over 2, which is 1 minus 0, which is 1. Okay. Oh, that's actually kind of cool. The answer is not pi anything. It's actually equal to 1. Well, that is definitely greater than pi over 4, significantly greater. It's also less than pi over 2, I should have mentioned. The average, if the only possible values the distribution can ever have are between 0 and pi over 2, it would have been absolutely ridiculous to get something that's outside of that interval. So between pi over 4 and pi over 2 is exactly where we would expect to see this average. So in fact, it says that the average value is right here of this distribution. Now, this doesn't mean that half the time it's less and half the time it's greater. The mean is on average. If I did 1,000 ones and I looked 1,000 versions of this experiment and I calculated the waiting times, then I averaged them, this is what I would expect to get. It's an expected average time. It's not the same as the median, which happens to be the next question. Okay, this is the mystery m, let's say, that divides the area in 2, because by median we mean that some mystery time so that the probability of being less than the median is half and probability of being greater than the median is half. Okay, you might have noticed when you start doing integrals and areas and stuff in most calculus books, they give you these weird questions like what's the mystery x value such that that it will divide this region in half, and it's like, oh, it's kind of a cute extension of the usual problems in area. Well, this is a place where this really means something. It's called the median. Okay, so we have a mystery m here, and we want the integral from 0 to m of sine t dt to equal 1/2. 50% of the probability should be up to there. We could also do it as m to pi over 2 is equal to 1/2, but that seems a little more complicated. Okay, well, we can do that. That's again minus cosine t. It's getting kind of repetitive here, I know. From 0 to m, the mystery, is supposed to be 1/2. And so that's going to be, the minus is going to flip the order. So it's going to be cosine of 0 minus cosine of m is equal to 1/2. Okay, but that's 1. 1 minus cosine m is 1/2. And so cosine m, rearranging things a little bit, cosine m is also 1/2. Happens to be, there's no guarantee that this would have been a nice number, but it happens to be that m is the mystery angle, mystery thing in radians, whose cosine is 1/2, and that's pi over 3. Okay, so that's kind of nice. Often those calculations would be kind of nasty, maybe even have to do it numerically. But it looks like pi over 3, which is a little bit bigger than 1, that actually gives us the halfway mark in terms of the area. So it turns out the median and the mean weren't super different. They certainly could have been somewhat different here. But it turns out that pi over 3 gives you the amount that's going to be half of the probability. Okay. Notice we could have already said the median, just like the mean, must be beyond pi over 4. We already knew the probability of being greater than pi over 4 was 70%. And so we have to push that line up further to get only 50% above it and 50% below it. So that's an interesting answer. Okay, so half the time I'm going to weight less than pi over 3, half the time I'm going to weight more than pi over 3. Okay, one last one. Just extending that same kind of idea. Suppose I want to be 95% sure that I get my pudding by a fixed time. Okay, so that maybe I do have to leave by some time, and I want to make sure that I'm only going to miss the pudding 5% of the time. Okay, what should that mystery t be? It's a very similar calculation. It's just going to be integral 0 to t of sine t dt. That's the probability, and I want that to be 0.95. Okay, so once again, it's going to be cosine 0. It's going to be 1. It's just the same. The left-hand side is exactly the same, basically. 1 minus cosine t is 0.95. So we want cosine t to be 0.05. And now it's not a particularly nice number. It's the inverse cosine of 0.05. But we can evaluate that numerically. And so that's about, I should wait till about 1.52. Notice that's pretty close to 1.57. Makes sense. Or is it approximately? There it is. If I waited to 1.57, I'd have a 100% chance because that's the end of the interval. But if I wait to 1.52, then I've got 95% of the area under this curve. Turns out that this kind of thing, 95% sure, that's a very common thing in statistics where we use probability distributions in statistics. What's sort of a 95% confidence interval? Often you use those with different distributions like the normal distribution. But this is the same general idea. All right, that's it.